Meet up here, and he's going to give us a talk on domain-specific languages and how we can use them to improve our lives too.
Okay, so hi everyone. So this talk is a bit dense and mathy. Let me make two. First off, if you don't know that much Haskell, that's okay. If you know Haskell, it won't help. I asked that basically, hopefully you're going to be able to hang on, get some bits of it. I'm being ambitious here because that's what I wanted to do, and if you take away some pieces, I'm going to be very happy. If you know most of this already, I'm going to apologize for what I'm about to do to it. All right? So, you know, that's the other side here. There's a lot of material, and I'm going to try to get through it at a good pace. I'm going to try not to get too detoured during it. And a lot of good references. It's stuff I'm really interested in. So the story here is it really started out, and this is the talk I gave at Lambda Jam, more really trying to be about my experiences building actually, it turns out a lot of domain-specific languages over the years, now that I think about it. And what I've sort of learned from it in a more sort of practical thing, and I'll sort of shill my JMacro library for programmatic generation of JavaScript, which I'll promote it by giving a talk that relates to it. And it turns out that's really not in the talk anymore. Because I started to think about what does it really mean to talk about domain-specific languages and languages. And you know, I could get up and give these Yoda-like sort of prescriptions about, in my experience, this works and that doesn't, but they're just sort of like, they're not very well grounded. So I started to think about how to ground my experiences in intuition, and it took me down a much more formal route. And I'm going to try to give the formal stuff and then relate it back to practical stuff in some sense, and we'll see how successful we are. And we're going to start out with just a motivating example, numbers, all right? The math that we're talking about isn't about numbers, but numbers are a good example of math, so we'll talk about those. All right. Numbers have digits. We're going to start slow. There's some digits. There's all the digits, in fact. Here's some numbers that we can make with digits. Okay, 3, 34, 25. We're going to call the numbers with only digits naturals. So among the branches of math I'm abusing are analysis here, okay? Here's some numbers that have some digits and then a period and then some more digits, okay? So those are different than the other numbers. Numbers with digits and then a period and then more digits, we're going to call the reals. Okay? So now we've got two types of numbers. And actually, you only need two of anything to get really interesting results. So that's what we're going to stick here. We can take the reals, we can send them to the naturals. Well, we're going to take away the dot and all the digits after the dot. And if those digits are non-zero, we're adding one. So we're actually going to round up the ceiling function, okay? And we're going to call that forget. And it's weird to forget upwards, but there's a reason we're doing that. And we're forgetting the fact that there's stuff after the period, really, by just sort of like rounding it up. Okay? So we can also go the other way, take the naturals to the reals. This one's easy. You give me a 5, I give you 5.0. Okay? We're going to call this lift, or free. All right? And you get it for free. Some numbers are bigger than other numbers. You can do a lot with just numbers. All right? And the relationships that emerge get complicated, but I like to keep it simple. So we're going to have a sucker called a preorder. Those of you that were at Dustin's talk will remember that he talked about preorders there too, and as it turns out, for similar reasons. So preorder is just some ordering where you have only one operator, which is less than or equal to. And it's transitive. So if x is less than or equal to y, and y is less than or equal to z, x is less than or equal to z. But you don't have this other way around. So you can't say that, if it's not one way, it's the other way. Two things just might not have any ordering relationship to each other. X is not less than or equal to y, and y is not less than or equal to x, right? They're just living in their own sort of places in the ordering spectrum. Numbers have a total order, so they obviously have a preorder, since a preorder is just a much simpler thing. So, but we only really care about preorders. Okay. So now we can do something complicated with our simple stuff. We're going to use a funny notation. I'm going to say x dot and y dot are elements of the reals because it's x dot something, right? It's 5 dot something. X and y are elements of the naturals. So we have lift x, right? So that takes a number and it sticks a 0.0 after it, is less than equal to, some number that has 5.5 or something, right? Now, that's actually going to be the same thing. I'm going to make that claim. If this is true, then this is also always true. So that x is less than or equal to the ceiling of y dot. So if I have lift 4, is less than or equal to 4.5, right? Then that's going to imply that 4 is less than or equal to 5. And this is less than or equal to in the preorder on the reals, and this is less than or equal to in the entirely other preorder on the naturals. Two different less than or equal signs, two different type signatures. And if one is true, the other is always true, and this goes in both directions. And here we've got the same thing, but I just rewrote ceiling to forget. And here we can say that therefore, this relationship on these values is actually the same as a relationship on these two different functions that are on the reals and the naturals. All right? So this is actually, now that's something pretty sophisticated that we can get to. We call it a Galois connection. And it's really common, it turns out. And we're going to talk about a lot of Galois connections in this talk. Everyone, I just want to make sure people are sort of cool with this notion. Like, you can just make up some numbers and try it. This is always true. I make this claim. And there's a lot of other Galois connections we have that we'll get to later. And this one is interesting, and this is why we're rounding up and going to ceiling. It's not any old Galois connection. You can do a lot of Galois connections. It respects semirings. If we're rounding down, you have a perfectly good Galois connection, but it doesn't respect semirings. If you round up, you can not only lift less than equal, you can lift plus, you can lift times, you can forget plus, you can forget times, and all of these equations will still hold. So I can take any equation with plus and times and all this stuff on this side, less than or equal to something there, and I can do the same trick I did before, just like I did with individual numbers. I can do it over expressions of numbers with plus, and times, and it always works. Because when you're taking things up, the stuff that you're forgetting is enough to preserve the ordering information you need. You're never going the wrong way. And you could think of other Galois connections that make this sort of more degenerate and obvious. Like you could have one of them being the trivial ordering with only one object. Right? Anyway, so now let's look at this one. Convince yourself that this is true. You buy it? Right? 1 plus 4 is less than 2.9 plus 2.9. Less than or equal to, sure. That means that 1 plus 4 is less than or equal to 3 plus 3. That's why we have to round up, to take those guys up, and then these guys there. Good stuff. We have another one. Log and x. This is actually an isomorphism, basically, but we're going to say they respect semigroups. So it's the same thing, but you actually can't lift times as well. You can only lift plus. Times gives you a min plus semiring. It's a lot of fun, but we're not going to go there. But you have the same story, right? If I can do something with, numbers in the reals, I can take the logs of them, and my ordering relationship is still going to be total if I start, at the right point, and positive reals, whatever. And then we also have the same sort of relationship where if I've got some equality that holds in the log domain, I can translate that to an inequality that holds in the other domain, right? When you take it back out of the log domain. It's an isomorphism. All right, guys. How many people know the answer to this question? 98 times 34, is that less than 1, 2, 3, 4, 5, 6? Do you know the answer to that? Yeah, all right. Keep your hands up. You all know the answer to this. Don't be modest. All right. How many people multiplied 98 by 34 to figure out the answer to this question? All right, yeah, a lot fewer hands, right? Well, nobody is raising their hands anyway. You're not a very interactive audience. They should have come down. Now, even if you multiplied it out, did you then go through and then look at both numbers and then subtract 1 from both numbers, one at a time, and see which one hit 0 first? No, you obviously did not, right? So you knew the answer to this question without multiplying those two numbers out. How did you do that? How did you figure this out without actually having to perform a calculation? There's a knowing beyond calculating. I said I'd go light on the Zen. I didn't say it would have no Zen. All right? There's a knowing beyond calculating. We can answer questions without doing the entire computation that we're trying to answer. And that's an adjunction, writ large. It's a way of only asking the part of the question you really need to ask and throwing away the rest of it. That's one way to think about adjunctions. Now, this is a sample derivation of how one might have really gone about this, right? So you've got our Galois connection rule up top. And that's our general thing of all Galois connections. We have 2 Galois connections, and we're going to go through one of the Galois connections. We're going to take the log, we'll say base 10 of both sides, so that, you've basically counted the digits, because log base 10 is the count of the digits. because we're going to first take the log and then we're going to take the ceiling. So we've got basically, so that gives us the count of the digits. We can compare the count of the digits, then take that back up, and then we get our answer. So what we've done is we've gone through 2 adjunctions to get the answer. Now, when you did this, you didn't say, I'm going to go through 2 adjunctions to get this answer. And you didn't say, going through 2 adjunctions to get this answer is going to be way easier than just multiplying some numbers. But in fact it was, and you did. So elementary school shortcuts are adjunctions. We use these things all the time. We don't think of them that way. But you figured this out, and you didn't even need to actually count the digits. You could just look visually and say, okay, I'm just going to mentally smush these things together and see how long is it, right? And then this one is longer than this one, and that means it must be bigger. Because that's how numbers work, and you figured that out when you were learning multiplication. So this stuff is really core to how we actually think about calculating all the time. And so this is what I'm going to claim. There's many ways to represent numbers. They can be notches on a stick. They can be measurements of a ruler, right? They can be Roman numerals. But when you actually have these things written in base 10 with these Arabic numbers and whatever, that's actually a really good domain-specific language for representing numbers, because you can do things like that with it. And that's an important intuition, that there's a reason we prefer that to notches on a stick or many other ways. And so when we're talking about building our languages, we want them to have the same magic property, that you can look at an equation and immediately see a lot of things about your functions, about your equations, without actually going through and doing all the work of actually performing the computations that a computer would do to get that answer. And that's the core intuition here behind what we want to talk about. So now we're going to do injustice to categories. Yeah?
So there's some kind of alignment here between topography and semantics, right?
We can come back to that. So hand-waving categories, they're things that they have objects, they have morphisms, and they have conditions on these morphisms. So you've got a bunch of stuff, you've got arrows between them, and you have to have identity arrows from each object to itself, and the arrows have to compose like you'd expect. That's not going to explain categories. It's enough to get us to the next thing, which is functors, which I'm also going to do injustice to. They take objects to objects, arrows to arrows, and they preserve identity and they preserve composition. So now I've got one bunch of stuff here, one bunch of stuff there. Each one of these guys is going to map one of those guys over there. Every arrow between these guys is going to map to an arrow over here. And it's going to preserve those nice properties that we wanted before to make equations look equational. And we don't care about functors because we care about adjunctions. So, all right, so again, this is where the bus turns and everyone falls off, and that's okay, we'll come back down again. But, and we got to get through this fast, and so I'm not going to tell you the real story about adjunctions. All right, what I'm going to tell you is adjunctions are a pair of functors, and they go one way and they go back the other way. And you all, if you've got any two categories that are exactly the same, you have a bijection, and that's a functor, or an adjunction, in fact, right? If everything here can map to everything there one-to-one, and then one-to-one we can map it back, we can take all the arrows over, we can take all the arrows back, right? That's an isomorphism, that's a bijection, everything's the same. An adjunction is when you start to sort of loosen the screws on that notion, is one way to think about it. And you write F, that little turnstile is adjoint, left adjoint to G. And so F is going to take stuff in some category to some other category. G is going to take it back. You've got this looser notion where if I go via F, then to G, then to F, then I can sort of eliminate this and come back, and I've got the identity. And this way I can do that, and I got the identity. And so they have this notion that if I go there and back, I might not come back to the same place. But if I keep doing it over and over, then I am going to come back to the same place. And one intuition that I think is pretty good for this is if you think of a parser and a pretty printer, right? If I parse your code, I might pretty print it with a different indentation style. But then if I parse the code again that I pretty printed, and I pretty print it again, it should probably look the same after that, right? That's an adjunction. I mean, it's actually left retry, but we're not going to. But that's a notion of an adjunction that's very easy to hang on to. Yeah.
Sorry, what's the difference between this and a bijection?
A bijection is they're exactly the same. Adjunctions aren't exactly the same. You can get information, you can lose information, but and what we really are going to find out is all the adjunctions we care about are sort of fancied up versions of the Galois connections for the purposes of this talk. And
so you're saying like the fixed point of the full traversal is...
You don't even need a fixed point. You just need to make one round trip and you're done. You just need to go F to G to F again. And then after that, you can keep going to F to G. So we can come back to our Galois connection example. It's a very good one, right? Because if I go the forgetful way and I take 3.5 to 4, right, then I come back by making it 4.0. Now, I can keep going around in a circle. It's never going to go anywhere but 4, right? And you have that in the other direction too, and even easier. You know, start with 4.0. It'll never go anywhere else. So in general, you have, and that's why I'm using the words free and forgetful. And they're totally, it's an intuition. It is not a formal way in itself. You can formalize, we're not. There's a notion of one direction in one of these adjoint functors will tend to be the free one. That really doesn't screw up your information. Right? If you think of one of these categories somehow bigger or containing more information than the other, the free way will sort of in general like be the simplest way to sort of take the thing with less information and just shove it into the thing with more. And then the forgetful one will tend to be a way to throw away certain bits of information and flatten stuff out. These are not precise definitions. They will mislead you, but they are good enough to think about the things we're talking about with and the types of Galois connections we're working with. And they get you pretty far. So that's what I'm doing here is and we want to move on. This is my joke. This is what happens when you go to Wikipedia. We're not going to do that way. Some people will claim this is the easier way. All right, so how do we treat a Galois connection as this adjunction guy that we just introduced? We're going to say we have two categories. They're both of partially ordered sets. So they have objects. The arrows between objects are going to be simply, less than or equal relation. So we've got the line of real numbers, and 1.5 has an arrow to every number greater than it, and no arrows to anything else. All right. So every object, in fact, has at most one arrow to any other object. Right? Now, this gives us a Galois connection if we look at our free and forget on that. And you can sort of, and it's actually pretty visually, if I had a lot more pictures, it might be cool. I'm sorry, I'm just going to wave my hands. Because there's this visual notion where you can see the arrows sort of flattening out into a smaller set of arrows when you forget the stuff and when you just sort of round upwards. And that it's a way to think about what's going on. And so you have the lift is the left adjoint to ceiling, exp is the left adjoint to log, free is the left adjoint to forget. So this is, I sort of ran ahead of the slides here. These are the intuitions I was talking about. Eugenia Chang points out, if you want to remember which the free side is, left and free both have 4 letters. So that's actually a good thing to know. One side is a smushy side, one side is just, the free side. The smushiness all happens in one direction. You're sort of rounding up along with that plus and times, because plus and times make things go up as well. And every left adjoint uniquely has one right adjoint and vice versa, if it has any. So, okay, so now let's come back and try to put this to work with programming languages. Good luck. So every language has a theory. This is a big statement from model theory. And this is definitional, really. We're going to say a language is sort of the set of all the things you can say, and a theory is what you can say about those things. So every language has at least one theory. One way of sort of talking about what it means. Otherwise, it's not a very good language. It's just a set of symbols. Some languages have bad theories. I was going to go into this more. Now, this is really special. This is the extension language for PHP Bulletin Board. And it's an XML document that contains within it XML information about regex that you search for in order to find blocks of code and replace them with other blocks of code. And then it will intercept all calls to this PHP file and execute this at every call in order to then transform it. And this is how you add an extension module to PHP Bulletin Board. It has a theory, okay? But the only way to know what it is, the theory, the meaning of this, is determined by the exact piece of code that it's intercepting and everything else that's happening in the environment and actually stepping through all the replacements and then seeing what happens afterwards. So there's a theory for this. But it's the theory of executing it and watching what the computer does. So that's maybe not a big help. All right, more Zen. Things are similar, therefore equational reasoning is possible. Things are different, therefore equational reasoning is necessary. Okay, and so this is what we want to balance between, is we want a language to have a lot of theories. We don't just want it to have the trivial theory of just execute it and see, turn the crank and see what pops out the other side. You want a lot of these nice sort of elementary school visual shortcuts and other notions so that people have an intuition working with it. And also that so computers can analyze it statically and learn a lot more about it. We want languages open to multiple non-trivial models. And we can use adjunctions to talk about what it means, sort of upper level. What it means to have a set of languages open to multiple non-trivial models. So there's the famous adjunction between syntax and semantics that I now present to you. Okay. Yes, now you have seen the adjunction between syntax and semantics. What are syntax and semantics? Gosh, let's sort of explore that. Let's go back to models and theories first. Model takes a sentence, which we haven't really defined, but we're going to call it, a sentence is like an English sentence, but we don't want to do English because no one knows what it means. It's like, it's an expression in first order logic or something. A sentence is going to be some notion of a complete expression. A model is going to be the thing that's going to take the sentence to some values. So we'll say we have a model of a language in some domain. We have a model of first order logic in the domain of the Booleans, so that I can take every expression and this model is this expression true or false, right? What does it evaluate to? So a model is some notion of evaluating it, but it's not necessarily the usual evaluation. The theory here is slightly different than how I was using it earlier. This is sort of more formally, we're talking about is a set of all the sentences that you want to be able to express, right? So, with first order logic, they're probably infinite, but you can sort of enumerate them from the beginning and you'll just keep going forever. But it's just your collection of all your sentences, and then you could say, well, the collection of all the sentences using no more than 8 or no more than 10 or maybe no more than 12 connectives, and just keep adding one each time, and then you're finite as you grow. So syntax and semantics are functors, right? If they're adjoint, they must be functors. And what they do is they either take your models to your theory, or your theory to your models. So they take sets of interpretations to sets of sentences and back and forth. And I claim there's a Galois connection. I don't just claim. We know there's a Galois connection, or an adjunction, between these two things. And when this was introduced, people also called the syntax functor the structure functor, which is a nice way to think about it, because it's giving structure, right? Concrete sentences to your models, your semantics. So here's the sort of way we would tend to write a theory in Haskell. Right, this is our simple expression language. Here's an ADT. An expression is going to be, some value, which is a double, or it's going to be the product of two expressions or the sum of two expressions. We're not going to do that. We're going to make it hard. This is the fixed point of a functor representation. This actually gets to Brian's talk on using types, because this has a neat property we're going to get to. So it's sort of the same thing, except everywhere where we recurred, we no longer recur. We just leave a hole, right? So it's expr of something, and we just leave a hole there. And then we're going to introduce our fixed point thing that's going to take this type, and we'll have an expr of exprs of exprs of exprs all the way down to infinity. And that's what this fixed point lets us write, if you haven't seen that before, right? So this is just a way of expressing that you're going to nest exprs all the way down. Here's a sucker called mu. Let's sort of wave our hands over this. The important thing about it, I'm sorry, there's a lot here. Like I said, I'm getting a lot of looks.
Maybe the size of syntax. It's still very difficult.
Well, look at the types. Don't look at the function itself. Look at the types. And look at the claim we make. Ignore the implementation, which basically it's better to figure it out just by trying to write it and following the types until they get you there. Look at the claim it makes. Mu is something that has a type for some functor of A. Well, we're not saying f is a functor, but I'm going to say it's for functor of A to A, right? So if I have some container containing some value, I can give you, at some locations I will always give you that value. So if you give me that, I will then give you a single value. And I'm claiming that fix and mu, fix of some functor and mu of that functor are isomorphic. We can take fix to mu, we can take mu to fix. We're just going through it because it captures, it's a fold. This is sort of your canonical fold, right? I tell you how to deal with one level, right? Fix of f is really f of f of f of f of f of f of a, right? But I just tell you how to take a single fa to a, and I can collapse the whole structure. Right? That's sort of how a fold works. And that's the story that we've got going on here. So we're going to take our fixed point construction of syntax trees, and we're going to turn it back into model theory just by using some type aliases. So we say the fixed point of a functor is the same thing as a sentence in the language of that functor. All right? So a sentence of our expression is, you know, all the levels of it, even though we've only described it in a finitary way with a, you know, little sum of products construction, as they call it. We're going to have run interpreter, which will say, if you give me a model, right, which is just any f of a to a, right, which they tend to call in other parts of CS, they'll call these algebras. But we're going to call it a model because we want to be in model theory land. So if you tell me the, you know, one-step reduction of some expression, right? So I can take an x per f of doubles. So if we come back here, right, then these are just all doubles. So I only have to evaluate it one step at a time. If I can do that on one level, I can do it on all the levels. And that's running an interpreter over a sentence. And what the types bias is if I just have any function that takes any sort of sentence, that it can look here, it can look at the top, the bottom, do weird stuff. It doesn't have to be local, right? I can say, I'm going to return a result only if there's something 7 levels down and something else in this other branch 4 levels down, right? As long as you're only working at one level at a time, you actually get the property that we call referential transparency, which is that the meaning of every expression is only determined by its children. And that's something that we care about a lot as functional programmers. So this is the interpreter I was describing. I just tell you to take some f of 2 doubles, right? And I can add them, product, I can multiply them. Val, I can do that. Now I can construct a really complicated expression with a lot of different syntax, right? You know, x plus y times this plus that minus, well, I don't have minus, but you know. And I can evaluate all of that, and just using these rules alone, and nothing else, and this little mu construct, this fold, I can actually interpret my entire language. So I don't have to explicitly codify the recursion. The definition of that gives us the recursion for free. All right, wow, okay. Models of adjoints, wow. So we've got to remember what adjoints are again. So we have a model, it's just f a to a, right? It's just a one-step reduction. We're going to have the opposite of a model. It's going to send an a back to an f of a, okay? So the adjoint is going to take any f of a to a and going to flip it around. I make the claim you can always do this. How are you always going to do this, man? Well, here's the interesting thing. Our FAs are really small, all right? You know, if we assume that, you know, our A is from some finitary domain, so I mean, maybe doing doubles is not the best, but you know, there's really only so many. There's just a lot of them, right? You know, we're really limited to 64 bits. And our F is going to be a sum of products, so there's some finite combination. So I can list for you every single FA. It might not be very efficient, but I can always give you a procedure that will enumerate every FA. Now, if you give me an FA to A, right? I can just keep looking for the function. My function that I will give you back is the one that for any A, right, or that will always look for the simplest FA that it can inject it back into, right? So you give me this function that says it takes an FA to A. Now, I'm going to take an A. And I'm going to say, give me the FA that generates that A. Well, which one is it? I don't know. Let's try them all until we find the first one that works. We're allowed to do that. It's all final. So I'm not claiming this is an efficient function, but you can do it. And that's what's important. You just find the minimal sentence that yields that A by listing every single one. Or in fact, not sentence here, just one-step reduction. There we are. And that actually turns out to be, very loosely speaking, normalization by evaluation, which is pretty amazing. Now we can add something on top of this, because what we've done here is, right, find sentences, fix adjoint model. Okay. Now we have, models have validity. Now we're getting, just add one more piece on top. I'm going to give you an answer in some domain, but you know, maybe that answer is a Boolean, right? It's going to evaluate the true or false if it's a logical formula, right? So true and true is true, but true and false is false, right? And so I'm going to say whether or not that's true. But maybe it's another sort of judgment entirely. That's going to be some other notion of validity, like it's going to be valid by some typing relation or anything else. You know, another example I'm going to have is does this evaluate to 0? That's a fine thing to ask about something. Is this a zero, does this function have a 0 there? So we can take, if we have an eta bool, we can take any model of f of 8 and make it just a model that, you know, has a Boolean in its domain. So now we can write semantics and syntax, the functors that we wanted to start with. All right? We're going to say, we take some test, some validity notion. We have a set of all these sentences, right? So there's a whole bunch of things, and I want to claim these are all valid. Now, I can generate the set of all the models. I just enumerate all the models. Remember, it's not very efficient, but I can do it. So I enumerate all the models that will make all of these sentences true. And that is semantics. The full set of all the ways that we can interpret things that will obey some validity relationship. And syntax goes the other way. I have the test, I have my set of all the interpreters. Now I'm going to list every single possible sentence. And every sentence that satisfies all of these different guys, well, you know, he's going to be valid. And then he gets to go in the set. And this is a Galois connection. Okay? This is an adjunction, and this is a Galois connection. Because it tells you something that we actually know a bit. The more models you have that you want to make true, the fewer theories you have, the fewer sets of sentences you have that can satisfy all of those. Now we think about this in a very particular way when we're talking about Haskell, right? Because we have functors and we have monads, right? We have a lot more functors than we have monads. Well, why is that? Monads have more laws they have to satisfy, right? So the more laws you have, the fewer things that will obey them all. On the other hand, the more things that you will have, the fewer laws you can say that are going to be true of all of them. And that sort of relationship between orderings, and here we're doing set inclusion, that's a Galois connection. It's the same sort of thing that's going on. And that's actually an important result to think about when you're designing a language, right? You know, how many things do I want to be able to express? The more things I can express, the less useful the language is in a sense. Because, you know, if you can express anything, then, you know, you can't really say very much about it. The more restrictive you make it, the more you can analyze it, the more claims you can make about it, or if you want to have some subsegment or a combinator library, same thing. All right. So here's an example that actually touches on but doesn't take us to actual Galois theory, which is language is polynomial expressions in 3 variables. So you've got, you know, x, y, and z, right? And you've got, you know, some number times x plus some number times y plus some number times z. And that's your language. Your semantic domain is the reals. Your model, right, your way of evaluating it is you just plug in. It's a triple of numbers that you plug in for x, y, and z. Right? This is now you have linear equations, right? Linear algebra, right? And so validity judgment is this 0. More formula to satisfy, fewer assignments work, right? You know, if I just have, you know, 3x plus 5y plus 2z equals 0, I've got like, I can just give you triples forever that will satisfy this. I throw in, you know, 3 or 4 or 5 more, you know, equations. Eventually I can't give you any numbers at all that'll satisfy all of these simultaneously. So you have this, that's maybe a more intuitive way for...
Tiny irrelevant. You said polynomial expressions.
Yeah, okay, sorry. I'm just doing the unary ones. We can do the full polynomials, but I sort of simplified between here and there in my brain. But yeah, so we're just going to do linear algebra. Same works with polynomials, right? But that's a good intuition if you've ever done linear algebra, right? The more equations you have, the fewer answers you can get to them, and then, you know, you can do exactly this construction. If I give you 3 numbers, you can give me all the equations that will, you know, be satisfied by these, right? So you can go the other way as well. And that's syntax and semantics in simple domain. So now we go back to our adjoint properties. Right? You can make these loops around. You can find the models or the theories of the models, and that's the same as just finding the models once. You can find the theories of the models of the theories, and that's finding the theories. Now, why is this interesting? Why is this just not silliness? Well, this means that you've got a well-defined notion of the closure of the models. Right? So if I have this many ways of interpreting something, these are all the other ways that I might as well have. They come for free. I just already have them. And similarly, the models of the theories, I can take the closure of the theory. These are the sentences that if these are true, all the rest might as well be true. So that's where if you start with your, you know, sort of core set of propositions in the logic, right? You say all the others are derivable from these. That's that operation, is find me all the things there. Give me all the sentences that are true if these axioms are true. So this actually takes us, this is sort of unifying notion that lets us walk across a lot of notions in a lot of fields, which is why I like it. It's very general. And it lets you sort of think about them in a certain together way and code them up that way. We're not going to go into natural transformations. I will just claim that they have this type signature. They transform the structure at the top without being able to look into what the things are, because you've got that for all there, right? So natural transformations, as long as you have something of that signature, here's another expression. It's just like the first one, except we have ints instead of doubles. So what can we do? Well, we can take the ceiling and the log, just like we did way back at the beginning. And we can transform one into the other. Again, this is only one step, right? I haven't told you how to walk an entire tree of plus times. There's no recursion involved. One level to one level. And then you just use the machinery we've already built with the interpreter, and you can actually then do it recursively all the way down. So what does this tell you? Every theory is someone else's domain, right? We don't just have models over here and theories over there. Every theory is the target of someone else's theory is the target of someone else's theory. And chains of transformations give rise to chains of adjunctions. As we discussed, adjunctions compose F, adjoint to G, adjoint to this, adjoint to that, right? You can go all the way down, forget, all the way back up, free. That's still an adjunction. It's still a Galois connection. And so then you have a tower of semantics. And this is how we want to think about building domain-specific languages, or languages in general, and interpreters and all these things. We don't want to just have one relation where, we all already do this a little, right? Nobody wants to write the compiler that, reads in character by character and generates the bytecode as it goes. You want at least a couple intermediate forms, and you want some relations to hold amongst these forms. And the relations you want to hold are going to be the ones that preserve the semantics and compose down and compose up. I'm sort of going to skip the effects story, I think. Because we have referential transparency in what I'm discussing, and that it comes for free, which is really nice, right? At every level, you can only be determined by what's beneath you. Then you can't have effects in the way that we talk about them, right? You can't have something like some notion of global state. You can't even do the lambda calculus, honestly, because that involves generating fresh names, and you need some notion of, what a fresh name is, and names are an effect at that level. So, all right, so I am doing effects, I lied. So the brief answer, which we're not going to go into, is you make your semantic domain be something with monadic effects. And it's actually not that hard. But you can stay algebraic all the way up until that last point. And that's actually a real thing that it's good to think about. That a lot of people like to go in Haskell, and they start off, and they will immediately say, oh, I'm going to code everything up directly in the monad, right? That's going to capture everything I want to do. Except now you have the same problem as with the PHP thing. The only way to find out what's inside this object in a monad is to run the monad, right? It's too late. You're already dependent on the context and the effects. Much better to keep all your structure around as long as possible, and only at the last possible minute, actually go and introduce those effects so that you have to run them. Because there's a lot of times when maybe you don't even want to look at those effects. Maybe you don't want to run the thing. Maybe you want to find out something about it that you can find out without running it, right? What if it's something, a language that involves talking to a database in a couple places? I don't want to have to run it and go through all this stuff and be in this ambient monad context just to find out what databases it might connect to. Not when I can just traverse the syntax tree and find that out much more directly. And so that actually comes up a lot, is that you move in too early, and I've made this mistake before, into what you ultimately want to produce, because you assume that's the only thing you'll ever want to produce. You write a template language, and you say, I'm going to directly go into, the final stage where I'm going to produce something in the reader monad that will take all the environmental parameters, and I'm not even going to produce a syntax tree or anything. I'm going to parse directly into a function that will just execute everything. It's fast as blazes. It's great. It's just, I just produce a function at the end of my parser. Now someone says, well, what does it actually need in the environment? What are the environmental variables it's looking for? I don't know anymore. I have to run it and then see if I throw an exception when I can't find one. Because I screwed up, and I was so smart and so efficient, I didn't create an intermediate stage. So that's on the more practical side. But you can think about it in this more abstract fashion to try to formalize why that is we've ruled out too many interpretations too soon. We've ruled out too many theories. And here we are too. We've talked about semantic domains again for things that are expressions and referentially transparent, a bit with a little effects. But what if you want to talk about, programs in general? Well, that takes us to denotational semantics. That takes us to the motivating question for the talk that Dustin gave. That's where you start to get these questions arising. So we don't start with the theories if we're writing a mini language. We don't start with the syntax. We don't have this notion of a fluent DSL where I want to write, do this dot and then this dot filter that. right? And I've just basically, it's a DSL because I've given my functions English names, right? That's not a DSL. We want to start with the meaning, sort of the combinators that give meaning to what we're doing, and we want to sort of build out an algebra from that abstracts that. We want to build out some functorial or syntax tree type representation, and then we want to be able to layer the syntax on top of it that we want. So we want many layers, and it feels like more work, but it's not, because you can understand each layer, which you can't with these more complicated things. We want to write the theories that match our domain. We want to layer theories on theories. Each model disallows more sentences, provides more rules, right? Just like we parse first when we have syntactic correctness, then we type check second, and then that rules out more things, and so forth and so on. We want to include the AST. That was the lesson I learned. All right, so now I'm just going to talk briefly about, this is an example of this stuff. There's a library I built that's sort of like 2/3 done. It was a lot of fun. I got bored. But it's a good example of these sorts of things. So it's called ADF-DSFA for a darn fast discrete finite automata. And you've got applicative combinators at the top. They translate to combinators that build DFAs in Haskell. Then you have these things I call monadic transition collections, which are just ways of sort of dealing with naming effects, because the combinators will need to say, well, what's the end state of that? And then you have to pull an integer out to represent the end state out of the air, and then how do I know what that is so I can stick it onto the start state of the next guy if I want to connect up all these components of a DFA. And then you run the monad to get the plain old transition collections. You deal with the naming effects, take those, turn them to LLVM, and then using the LLVM library, that will turn them to bytecode and then assembly. So you can have a high-level parser library that compiles down to LLVM. Now, you can take the whole bottom part of this tree, starting with transition collections, and you just chop off the top, right? Because each of these things is independent. They have well-defined relationships. And now I can just take a string, use an existing library that can parse that into an NFA, like the regex TDFA library, and directly create the transition collection from there so I can execute. Someone else did all the work of, actually parsing a regex, doing the right things, building an NFA for it. And I can just piggyback on that and stick on a whole different backend, right? Because all the pieces you can just slice and dice and put them in anywhere. Similarly, you can start at the top, keep the top part, come down to transition collections, but instead of generating LLVM, you just do a direct interpretation and, do it slowly in memory. So that's sort of the thing that you can do there. When you start building in this way, you don't restrict yourself to just the top layer or just, one layer. You can plug in at whatever layer is most appropriate to have a lot of ways in and out of these things that capture things. And that's where a lot of the power comes from. Okay, yeah, we're not going to do abstract interpretation. I'm sorry, this is a whole other thing. I will say it is sort of neat and amazing. I'm not going to explain what this is. I will say it's neat and amazing that Galois connections are at the heart of the entire field of abstract interpretation. And if you go read any of the papers on this, you will find that out, that they explicitly model it with Galois connections. And then what abstract interpretation lets you do is find extremum of functions, find data sources and effects. Type inference is a form of abstract interpretation. You're just interpreting it in a different domain, right? You can guarantee safety of different sorts. You can perform partial evaluation and program optimization. These are all different ways of using abstract interpretation. They're all based on Galois connections and what we discussed, but I just don't want to inflict this on you guys right now. And so what we want to do is move from languages computers can reason about, which is part of what this is about, to languages that people can reason about. All right, and we didn't do monads, which is great, but I will tell you, every adjunction gives rise to a monad. Every monad can be factored into at least one adjunction.
At least two.
At least two adjunctions, pardon me, yes. And so adjunctions are everywhere once you know where to look. I hope I've given you enough of a taste of them that you can get to that. I call it, it's like the stage of a 3-year-old when you learn a new word, you start pointing, adjunction, joint. And hopefully that this talk has done so. The slides are online, I'll post the link. It's got things to read that are more coherent and proven.
All right, we got a few minutes for questions.
Was there any significance in taking the detour through move from fix instead of just holding fix directly?
Probably not. I'm sorry. I think it's there probably was. It's neater to look at it just as its separate piece. But it's not important. You could have done it as a direct fold. You're absolutely right. Carter?
This is something that might be off topic, but first, actually really understanding abstract interpretation, is it probably a good idea to start with the original Cousteau paper?
I don't know. A lot of their papers are very expository. Because once Cousteau figured out abstract interpretation, he spent years just trying to convince everyone else all the uses for it. So he wrote multiple introductory papers on it.
Okay.
This one here that I like is good because it will actually walk through, and it does exactly this tower of interpretations. So it starts, and it's got like 4 different ways of giving semantics to a program, and it layers them on top of each other using Galois connections to get more and more granular as you go. So it shows sort of what I'm talking about.
So adjunctions are not isomorphisms. They are structure preserving morphisms. Is that true?
I'm not sure what it means to be structure preserving. They preserve some structure and they throw away other structure. They're not anarchic.
They're still functors. The functors, the 2 functors make up the adjunction. Those are the part of the structure preserving. The relationship between these 2 structure preserving maps is the adjunction. So you're talking about the relationship between these 2 things. That's preserving structure. Not itself.
It's not okay.
Just to make sure I understand, like, I think that you only lose once. You lose the first time you transition, and then afterwards you stay the same because you can always be fully represented in the former, in one of the representations. The other one, you lost that already. So
Well, that's the story, yeah. F.G.F can compose to just F, and G.F.G can compose to G, yeah.
Hi, this is I just indeed one doesn't have to know Haskell to grasp talk, but you should know what a broken topos is. But no, it's not true. It's not true. But
In that case, I can't give the talk.
the or example, which is even more primitive. So this is for people who haven't mastered Fortran or Basic. The or example is you have a bunch of dots called a set over here, a bunch of dots called a set over there, and then some of the dots are connected in lines. And I'll let you take it from there.
I'm not.
I mean, you did it. So if you take a set of dots on the left, you can consider the collection of the set of dots on the right, which is connected to everything in that set that you've chosen, right? If there's one that fails, then you don't put it in. But, okay, now if you go that way and then back again, that is the or example for some people who actually learn Fortran and for whom Lisp 1.5 is Lisp. That's actually the example of Galois Connections. It's a little less sophisticated than Galois, which has more structure. But that's the or example. And I just mentioned it. So that's all. It has, yeah.
So basically just the
Rick?
No, it
gives
you a closure.
I just had this right here. Is it so you're losing when you go, but what you're losing it like with this parsing, right? It didn't matter anyway. That was bad. Like things that we're losing were like all potentially incorrect states anyway.
But you don't know what you could be losing something good or bad, right? You don't know. You're losing something, but you could be, huh?
You couldn't interpret it anyway because the later stages don't know how to handle that.
Well, yeah, in that case, but not in general, right? I mean, anything you lose as you sort of go down, if you're only talking about programming language semantics and not the broader world of adjunctions, obviously anything you lose as you go down can't be that important because at the very bottom you have machine code that should still have the meaning that you, quote, care about. So you can't throw away the meaning of your computation. And in fact, looking at these adjunctions is a good way of saying, you know, getting more precise of what do I mean when I say the meaning of my computation. Obviously, I don't mean the white space, I don't mean the comments. Maybe one level down, I do mean the comments because I want to preserve the comments when I transform some stuff. But another level down, I don't care about the comments. Another level down, I don't care about where, you know, the braces were. Another level down, I care about even less. You know, but the point is you might want any of these levels. So, yeah.
So there's a really simple case of going from a set to a singleton set, right? Where as long as the right adjunction goes back to the maximum first set, that's an adjunction too, right?
I'm sure it is.
I mean,
The-
it's kind of trivial, but it's still true.
Yeah, I mean, it's another good way to do it is a lot of subset inclusion stuff, which is sort of what Jay was getting at. Because subset inclusion is a really nice partial order that is not a total order, and then you say I have a bunch of sets on one side, and then they're all related by subset inclusion. The other side I have, you want to do something really trivial. On the other set I just have one set. They all go here, and then this just goes back to the trivial set on this side. That's the junction. It forgets everything, but that's okay. Because you've forgotten everything, there's only one free way to come back. It's legitimate, it's just not useful.
When you gave a literal example, a little more structured, you gave linear, you have 3 variables, x, y, and z.
Yeah.
So on the right, the models are triples,
Mhm.
y, z, and reals. And on the left, if those things are if those things are column vectors, the things in the sentences on the right are row vectors. You draw an arrow if and only if, boink, you multiply the things so you get a scalar. If that's equal to 0, you draw a line between them.
Right.
And then you have, on both sides, you have this notion of closure. That's nearly the most primitive.
Yeah, that's a good one, because then you could say if I have these 4 equations, then any triple that satisfies these 4 equations will satisfy these zillion others. Or
I suppose another way to say what you're forgetting, maybe if your first set is all of the code that produces a diagram, so you have a bunch of different ways of producing the same diagram, what you're forgetting is that which makes these representations different from each other.
well, that's one thing that you could be, that's one of the ways we want to talk about it. It doesn't, again, I mean, that's not adjunctions in general. That's a lot of times when you're talking about programming language semantics, that is what you want to talk about. But again, sometimes you don't, because maybe you want an interpretation that distinguishes between the guys that are really expensive and the guys that aren't. That's the advantage of being open to multiple interpretations, is you get, the more information you keep around as long as possible, then the more you get to like pick what you want to ask. And you can ask all sorts of things that you couldn't ask just as a result of running the program. And maybe you want to ask those, yeah.
Let's take one more question.
Yeah.
Okay, it seems from a programming language standpoint, you were advocating an approach to designing DSLs sort of along the lines of Oleg's final interpreters, Oleg, Kenshan, folks, Jacques Correct, that they worked with, which says what we should do is we should define the semantic functions that we want. And it's a wonderful thing, and I've played with it a lot. It seems to be hard to implement in practice, as it's hard to make a lot of the transformations that you want to make between various internal forms along the stack, as you showed. Have you tried doing? Have you have your own ADF, DFA?
I'm actually advocating the initial. I'm advocating the initial algebraic approach.
Okay.
Not the final approach is really neat, but like you said, it's got some quirks. The initial algebraic approach always lets you sort of. But what I am advocating is doing it. Maybe you don't actually write with fixed points. They're a pain. They clutter up your code. But do it one level at a time.
Because what you said, that doing the semantic approach first is very much what they had advocated in their.
I think the design approach is the same, but I'm just sort of doing it in initial algebras, and they show their equivalent in one of the papers. But
So
this way gives you.
Fine, okay.
But your talk was precisely about the difficulty of, like, sometimes you do want to make these non-local transformations. You want to break referential transparency because you know that you can, because you're in some domain where you're allowed to, like numbers. And you're right. I've played with that stuff. That's why I left out that section. That's where effects come in, is you can wrap your target in a monad. And I have an interpreter for the lambda calculus I wrote like that. It turned out to be pretty elegant. I think the approach will scale to some larger things. But I'd like to work it through a bit more before I make any strong claims about it. So thanks, everyone, for bearing with that.